Hello, this is the Lab 1 hardware, and I want to point out a few different items on the circuit. First of all, we have a couple of LEDs, and I believe they're connected to pins 8 and 9. The red LED has two leads. The anode lead is the longer one, and it has to be in series with a 470 ohm current limiting resistor. This gives you about 7 milliamps. Same thing for the green one. Here is a push button. And one side of the push button is connected to ground. The other side has a pull-up resistor, which then goes to the input. So when the switch is open, we've got a logic high. And when you close the switch, it gets grounded. And that's going to let the software know that the switch is closed. We're testing for a logic low, and then it turns on the LED. Further over here on the right, we have the variable resistor. This variable resistor is going to adjust the output voltage somewhere between 0 and the supply. Nominally, the supply is 5 volts, but that could be a little bit less. In my case, it's 4.75. So this will, if I turn it counterclockwise, reduce the pulse width modulation output all the way down to 0. And if I turn it clockwise, it's going to increase it up to 100% and give me an output of around the supply voltage. The software is also determining if the pulse width modulation is greater than 50% or less than 50%. This little dial here on my variable resistor indicates the position, which is about halfway. Over on this part of the circuit is the low pass filter. And it is made up with a 2.7K resistor and a 22 microfarad capacitor. Be aware that this is a polarized capacitor, and the white stripe has to be on the negative side, and typically the longer lead of the capacitor is the positive side. Okay, so the resistor and the capacitor gives us that low pass filter. And the equation for the low pass filter is the FC, that corner or cutoff frequency, is equal to 1 divided by 2 times pi times the resistance times the capacitance. Okay, so now that we have all of that together, we can try it out. And I'll have another screen capture showing the signal output from the pulse width modulation. Here I have the pulse width modulation connected to channel 1. Here I have the average DC voltage being measured after the low pass filter connected to channel 2. Hello, this is the program for lab number 1, and I'm going to go through it section by section. Hopefully during the lab this will help you out. So to begin with, we have a couple of comment lines, and then the next 3 lines are telling you which pins are associated to the tags or the variables. So green LED to 8, red LED to 9, and so on. Notice the way I've written the tags, that the first word is lowercase, the second word is uppercase. And all of the variables are case sensitive. Okay, moving down, the void setup is the part of the program that's only done one time. This is a lot of configuration. So I'm telling the program we want to transmit serial data at 9600 bits per second. That's for the serial output. And then pin mode is used to define the direction of the signal on the pin. Now by default, the pins are input. So if we want them to be output, we must have this pin mode instruction. So we're doing that for the green, the red LEDs, and the pulse width modulation output. Pin mode for push button 1 is an input. So we need to have an external pull-up resistor. In our case, it's 4.7. And then on line 14, pin mode is the pulse width modulation output on pin 5. Okay, those are all things that are done one time in the setup. Then we're going to move down to line 16, and I'll just move it up a bit. And on line 16 is the looping part of the program that goes from 16 all the way down to 40, and then it's repeated again over and over until you press reset or restart or open the serial monitor a second time. So on line 17, what I did here was I first of all measured the voltage on my supply and then I typed in that value here because that's the reference also for the analog to digital converter. So we want to get that first. And then on line 18, that's where we actually read the A to D input, the analog input. And it's a value between 0 to 1023, and it's an integer value. That's why I've defined it with int at the beginning. On line number 19, that's a floating point variable, which means it's a real value. It has fractional parts to it. And when you divide, make sure that you use 1023.0 so that you do get a fractional answer. So what I'm doing with that equation is converting the integer value to a voltage, somewhere between 0 and the supply. Then I'm dividing that number by 4 because the pulse width modulation output only has a range of 0 to 255. So we're basically scaling it. And actually that's what happens on line 21. So you can see I've given you a choice here of using line 20 or 21. So you have to comment out one or the other, but you can try both of them. And then on line 22, what I'm doing is converting the value between 0 to 255 as a percentage, somewhere between 0 to 100. Line 24 to 25, here we're just modifying the state of the green LED based on the push button. So normally, if you don't press the push button, it's equal to a logic high, but when you press it, it goes low. And all I'm doing here is I've placed an asterisk at the front of the variable, which inverts the variable. So if I press the button, push button 1 state is a high, which causes the green LED to turn on. And then finally, on line 26, I'm outputting the actual pulse width modulated value to pin 5, which then eventually goes through the low pass filter. On lines number 28 to 31, I'm using an if statement, and I'm saying if the percentage pulse width modulation is greater than 50, turn on the red LED, otherwise or else turn it off. And then down below here on lines 33 to 38, I'm outputting the information. As you can see over here, I'm outputting that information. And the information I'm outputting, I'm starting off with serial print, the value of A0, the analog input. It's then converted to a voltage. This is where I'm testing my push button, and I'll press it so that you can see it changes to a high. And then when I release it, it goes to a low. This is my percent pulse width my pulse width modulation value, and then the percentage. So my variable resistor right now is turned all the way clockwise. Now, just before I do that, have a note that all of these statements are print, 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 except for the very last one, which is print line. Print line causes the serial output to move to the next line. So I have everything on the same line until that last statement, then it moves to the next line. The other thing I did to format it a little bit better is I put some spaces before and after the variable names, and then the variable actually gets printed. So let's see what happens if I turn the variable resistor counterclockwise. Okay, it's going down. Now halfway between 1023 and 0 is about 512. So I'm going to get to that point approximately. It's a little tricky with this variable resistor. Here I've adjusted the variable resistor so that I get 50% of the voltage. And that means 50% of the pulse width modulated value and 50% pulse width modulation. It all works out. If I turn it a little bit more, you see it goes down, keeps going down until it gets to 0. So I'm just going to adjust it upwards one more time. So I hope this little demonstration does help you when you do the actual lab. Hello, this is the PicoScope setup for lab number 1, and I'm going to go through different settings and setup for the PicoScope. And each PicoScope setup usually requires a vertical, a time base, and a triggering setting. So let's look at those 3. So first of all, the horizontal or the time base is set up over here. And since our signal is about 2 milliseconds we want to have the scope set up to 2 milliseconds per division. And that's what I have right now. So here are the divisions. So this is one of the divisions. Here's the next one. And you can see it takes about 2 milliseconds for the signal. And to change that, you can just click on this box, and then you can change it to 1 millisecond per division, or 2 milliseconds per division, and so on. It just took a little bit of time to refresh there, but that's 1 millisecond per division. So you can see it's taking 2 of these vertical divisions to create one square wave. Or I have 5, and you get many on the screen. You want to typically have somewhere between, say, 2 and 7 approximately on the screen. 2 to 10 would be okay as well. And then once I've done that, I want to look at the vertical sensitivity, which is right here. And so this is the vertical for channel A, the blue one. For channel B, this one. And I can change it to plus 5 volts per division, but then it goes way off the screen. I can go down to 10 volts per division or 20, but I prefer that plus and minus 10. So what that means is that it's plus 10 volts maximum and minus 10 volts minimum, but I've shifted the level of the signal a little bit. So what I want to have for this measurement is the zero reference to be maybe 3 of the divisions down. And I can adjust that just by coming over to this area with the number and moving my mouse up and down. Okay, but you want to have it set up so that 0 is on one of those lines. And that's for channel A. Channel B, I have set up to plus and minus 5 volts per division. So that means if there are 10 divisions, it's going to be plus 5 volts at the top, minus 5 volts at the bottom. So that's a volt per division. And that's what you can see here. I have 1 volt per division. On this scale, I had 2 volts per division. So my zero reference is right here, and that's where I want it, 1 division up. And I can move this up and down, okay? But you do want to have the 0 clicking on one of those lines. So that's my vertical. The next thing is you want to have a triggering point, because if you don't have any triggering, this is what happens. I'm going to turn triggering off, and it moves to the left or to the right. It just doesn't stand still or doesn't freeze. So you have to click on auto trigger, but just a warning here, if you do want to measure DC voltages, then you do want to select none. But I'm going to select auto. And now it triggers, and my trigger level is 2 volts. So that's the 2 volt point. That's the trigger symbol, the yellow diamond. It's also set up on channel A. My blue one is channel A. And the pre-trigger, what that means, and it's set to 20, is what percentage of the position from 0 on the left to 100% on the right is that set to. So I'm set at 10, 20%, which is right here. And that's a good setting because that way I can measure a signal and then see all of the rest of it towards the right-hand side. And I've set it up for a rising edge. This is what it looks like for falling edge. Doesn't really matter in this case. Okay, so auto, channel A, 20% trigger, 2 volt triggering threshold, and a rising edge. So those are all the trigger settings. The next thing I'll want to do is make some measurements, and I've set up many of them here. So one of them is the positive duty cycle of channel A. And the way that I did that is I went over to measurements and I found positive duty cycle. And let's see if we can find it here. It's right here, positive duty cycle. So I would have selected that. I would have also selected for channel A the top voltage. So that's this one here. And that's measuring the top voltage of the signal. And then we would have had the frequency of channel A, which is right here. The cycle time for channel A, which is the same as the period. And then finally, the top voltage for channel B. So I would have had to switch over here and selected top voltage, wherever that is. And really just measuring that average DC voltage. The other thing that you can do is use cursors. Okay, and for cursors, I'm going to show you a couple of them. They sit up here for voltage. So I can put that cursor on that top line, and I can move another cursor Sorry, it comes from up here, and I'm going to actually do it to the red side. There's one on the channel A and channel B, so I put a cursor there. So it's telling me that that DC voltage is about 2.6, and if I come over to here, you can see it's the same value. So this is the automatic measurement, and this is the manual measurement. The top voltage here was 4.7, and if I come down to here, you can see it's about the same. Don't worry if it's not perfectly the same, as long as they're about the same. So for the period of the signal, the cursor line sits over on the bottom left. So I'm going to line it up with that trigger point as best I can, and then move the second one. This will measure the difference between those 2 points. And you can see it's about 2.05 or 481 hertz. Now that's manually positioning it. The actual measurement is more accurate with the automated measurements. And you can see here it's 490, and that's what the Arduino is supposed to be outputting. So the next thing to do is to save all of this setup, okay? And you can do a screen capture using the tool in Windows called the snipping tool, or you can save it up here. But the other thing that's really important to save is go to Save and save it to a file called PS Settings, which is the PS Settings file. What that does is everything that you've set up, even your measurements, will be automatically saved, and you can save the file name. And I'm going to save the file name as lab1. So that way, if you only get half of this done, you can recall that file. So if I go back up to here and click on Open, lab1 presets are there for me, and it should come back with all of that information. Okay, and you can see that it's all done there. So the other thing you might want to do is click on Medium. That gives you a little bit more information, like the minimum, the maximum, the average, and there is a reset button to reset those statistics. But I'm going to stick with the smaller value. So just a couple of reminders. To set up the time base, or the amount of milliseconds per division, you can come here. Now you can also open this window, but you can also close it again and just click the plus and the minus. I find that that's actually a quicker way to do it. So I've done that there. Same thing for the volts per division. You can just click on the minus and plus. Okay. Now, plus or minus 5 volts is the best for our particular example. This is the generator. I'm actually going to turn it off, okay, because we're not using it in this example. And the trigger, these are the trigger points, and you can actually change the trigger level slightly up and down using these plus and minus keys. Okay, it's 20%. And if you want to take away the cursors, you can just click this button and move the cursors to the left and to the right. Okay, and this is what you want to screen capture for the lab. And just to show you what happens to the average DC voltage is have a look at the top voltage here and the positive duty cycle. They're going to change as I change the variable resistor. So if I bring the variable resistor all the way counterclockwise, I have a 0% pulse width modulation, and I'm getting 0 volts. So I bring it all the way clockwise. Okay, I'm getting the maximum voltage, which if I move my cursor up here, okay, so this is telling me that I'm getting about 4.7 volts. And you can see also the top of channel A is 4.7 volts. I hope this helps for doing lab number 1.